Hello, scholars. This is activity 4 for chapter 7. On page 15 of your study guide is where we're going to be referring to today. And the context we're going to look at is the SNAP program, which is otherwise referred to as food stamps for people who can't afford food. Sometimes the debate is whether we have enough money towards this program, or sometimes if you end up with too much allotment, we end up with fraud. Okay. So today we're going to look at, does this program provide enough to actually cover the cost of essential food items? So we're going to look at samples again, except this time we're going to be looking at a quantitative variable. We're going to be looking at the mean. And so just a little bit more background. These are the types of goods that when they talk about a bundle will cover. And specifically, this is a bundle that would create 3 meals a day, every day for a month. And so you can see this is what they would consider the healthy diet of meals. And so that's so what they call a bundle that they use to estimate the cost is this type of ingredients. One person, 1 month. So obviously a family of 4 gets an allotment of 4 for that if they have no income for one reason or another, or very, very low income. So the each bundle of goods, you would imagine going from one area to the next. San Francisco is going to be different than Minnesota for a lot of different reasons, and depending on which store you shop at. And so the average price gives us a better picture overall of what's happening with that. So when we look at the two symbols, when we're talking about trying to explain the difference between the population mean and the sample mean, we're going to use mu and x bar to do that. And remember that mu then is considered a parameter. This is for all the stores in the U.S., and then a sample is just a sample that we take from the population to do that. So when we talk about this particular problem, we would want to see, okay, so what are the key ideas in each of these things? What's the population, the sample, the parameter, and the statistics? So one thing you might want to do is pause and see if you can fill these in and then press play, and then we'll talk about each one. All right, so you could see that the population was all U.S. grocery stores, and the parameter that we want to measure is the mean cost for a bundle among all grocery stores, right? Now that's going to be impossible to find, right? So we're going to make some assumptions today, but later on, this is going to be the kind of the idea that we have to look at. The sample is the 31 randomly selected store locations, and that's the sample size n. And then the mean, the statistic we're doing, is the sample statistic of the mean, so the mean number of or the mean cost. And again, we found in the example they said that was precisely $201.24. So the question is this a really good estimate for what the actual average cost is? Well, that depends, right? And so a number of things. Do we know how accurate sample means are? Do we know how precise they are? Do we have an idea of, is this are we precise enough to know, is this good evidence that it's that we can say that, yeah, that is the average or not? So the idea is, let's take a look at a distribution of what sample means look like. Okay, now we talked about proportions, but let's use sample means. And here's the assumption that we're going to use for, we affectionately call it theory land, which is actually knowing the parameter. So 2020, we're going to use $194, and we're going to assume that that's the exact average cost. So we've seen this before, and the idea here is, okay, so you've got a bunch of stores. Those are the prices for the stores. We're going to take a sample of 16 and take the average of that sample of 16, and there's the mean. Okay, we're going to take another sample of 16, and then there's the mean. And we're going to keep doing that over and over and over again until we get a sense of what do all of these means, what do they start to look like? And we'll keep going with this, and what we start to see is, yes, the means start to have a particular shape. Notice that the center is actually the same as the actual 194, and there's some variation with it. So when we think about the these two, remember that the population is the individual store prices, right? The price for each bundle from an individual store, and then the mean is the means of the samples that we take. And a sampling distribution is all of the possible samples, all the possible X bars that could come from this population. Okay, so obviously we can see some things here, and again we're going to use this little preface: under normal conditions, that X bar just is normally distributed approximately, and it has a center that is right on target, right? It's that 194. And we would say that it's unbiased because it is exactly the mean of the population. Now, just a note, again, these two symbols mean different things, pun intended. It is the mean of all of the X bars versus the population mean. The population mean is the data. Mu of X bar is the average of all the averages. Okay. Now, if you look at the standard deviation, this is similar, that you divide by n, and so that tells us that or the square root of n, which means that higher sample sizes means less variation with that. And then again, just a note with notation is mu or sigma of X bar means the variability of all of the means. How far do the means vary? And sigma is the standard deviation of the individual data, right? How far these stores spread out from one another from the mean. Okay, and so obviously the higher the standard deviation, the more spread out this is going to get, and that means that the means are going to be more spread out. So that sigma in the numerator does have influence on that. So let's look at what else has influence, and that is the standard deviation. Or I'm sorry, the sample size, and how that's going to affect the means. So sample size of 25, has pretty narrow variation, and if you think about a sample size of 5, that's much larger. It's $11 versus versus $5. So we have much higher variation when we have a lower sample size. Okay, so again, since we're dividing by n, the spread increases as the sample size decreases, or you could think of it the other way as well. Okay, so here's the example we're going to use for this sampling distribution. We're going to assume that we did sample 31 grocery stores. We found that the cost was $201. So we want to know, is that seem unusual compared to if we make this assumption that the center is that the mean of all the stores are 194. So the question then would be, what's the sampling distribution? And so we want to think, okay, well, it should be approximately normal, right? And the mean is 194, and the standard deviation ends up being about $4.67. Okay, so if that's true, okay, and we can label those, then if we wanted to calculate the $201, that's where this is. We could actually see this is where those means would be, or more extreme. And so you really could just use a normal CDF calculation to find out that this is about 6%. So you can say that there's a 6.1% chance of getting a random sample like this that would have the bundle being worth $200 or more. So I noticed, or I said before, that these were under the right conditions, and so similar to proportions, these have to be under the right conditions as well in order for the shape, center, and spread to be what we think it's going to be. So the first thing is we need to have a randomly selected sample from the target population, or in the case of an experiment, needs to have random assignment. The reason why we need this is to ensure that it's going to be on target, right? If it's off target, or if it's unbiased, then I'm sorry, it would be biased if it's not satisfied, okay? Meaning it'd be off target. Okay, so for instance, if it's with random sampling, this is what we would expect to see, but you know, and the mean of all of the samples theoretically should be the population mean. But let's say that we, you know, use a sample only from the offices in San Francisco, or near the grocery stores in San Francisco. Well, it's going to be a higher cost of living, so theoretically the mean is going to be off target, the mean of all of the sample means here. And so if we think about that, if you don't do a random sample, you don't have the confidence that this is going to be unbiased with the entire population. Now, if we wanted grocery stores in San Francisco, do a random sample in San Francisco. But if you want one for the entire United States, you've got to randomly sample from the entire United States. So in other words, we can't be confident that that's true. Condition number 2 is the 10% condition, again, meaning that you know, these samples that we start to take are going to be independent of one another. In other words, the standard deviation, or how much the grocery stores vary, isn't going to change radically as we start sampling. And this is only true if the population is big enough, right? Or the sample size is less than 10% of the population. So I've said this both ways. You know, if the population is 10 times greater than the sample size, you're good. Or if you think 10%, that's fine. It is usually referred to as the 10% condition for that. So the standard deviation, just using the population standard deviation over the square root of n, really comes from adding the variances. In your book, there is a mathematical, you know, kind of proof of that if you're curious to take a look at it. So why is that, again, why is that important? And when we think about this condition, the 10% condition, it's so that we know that this standard deviation is going to actually be a correct calculation of how much the samples vary of that size. So the last condition is about shape. Is it a normal distribution? Well, there's actually two paths to this. When we talked about proportions, right, categorical, we said, well, n times p and n times 1 minus p had to be greater than 10 because it was a binomial setting. These are not binomial settings. They don't have success or failure. This is a value that is continuous, like cost. So we need to satisfy the shape that it's approximately normal one of two ways. Either it has to be from a population that is normal. That is very rare because a lot of times we don't really know about it. Or the sample size needs to be big. And when we say big, we say 30 or more, right? If that is true, then we know that the sampling distribution has that approximately normal shape. So, is it any surprise that when you take a normal distribution and you sample from it, that these are all going to look approximately normal? No, that seems reasonable, right? You select from a normal population, means from that are always going to look approximately normal. So that's not a big deal. Actually, small sample sizes, even as small as 2, will look approximately normal. So if they identify that you're selecting from a population that is normal, then this condition is already met. But as I said, a lot of times either we don't know or we suspect that it might not be a normal distribution. So it's dangerous to sample very small numbers because typically small sample sizes, if you're taking the means will model kind of the shape of the population. So if the population is skewed right, like this one, the means of sample size 2 are kind of skewed right. Now, if you go to samples of 10, we're getting better, right? But you can still see that there is still some skewness to that. So we can't be real confident that it follows that normal distribution yet. And it turns out that even at 25, we start to see things happen where we start to see a little bit more symmetry, and that starts to get us into that large sample size. Okay, now one of the things that we want to emphasize is, okay, so why are we using this rule of 30 to do that? And again, the concept here of non-normal populations, as long as you sample large enough, it's going to be approximately normal, is the idea of the central limit theorem. And the central limit theorem doesn't say any number. It says when n is large, because it sort of depends on what the population looks like, right? If the population is close to normal, you don't need a really large sample to get you there, right? However, if it's strongly skewed or it has some huge outliers in it or something like that, you're going to need a bigger sample in order to get there. And so the central limit theorem really doesn't talk about sample size. What we use, and what generally is the kind of the given rule, is 30 is your target, right? If you can get greater than 30, you have a higher confidence that sampling distributions are going to be approximately normal. Does that mean that you can't assume or at least work with a sample of 25? Not at all, right? You could still do that. One of the things you'd have to make sure, though, is that, again, we'd have to maybe note that the sample size is fairly small. Maybe we even look at the sample data to give us an idea, do we have some sort of skewness with smaller sample sizes? And we'll talk about that. Statisticians have worked with that problem as well. So the idea here is, if we can know that it's approximately normal, this is really helpful, because again, we don't necessarily know when we're sampling from a population. We might be able to guess what its shape is, but we're not really sure. Okay, so just like with proportions, with categorical variables that you might be saying yes or no to, when you're doing quantitative variables like mean, and you're calculating the mean, there are 3 conditions to help us be sure that the 3 parts of the sampling distribution are actually do what we predict, right? So it needs to be a random sample, the 10% condition needs to be met, and it needs to be either they tell you that it's normal or it's a large enough sample, and greater than 30, and it's approximately normal then. Okay? All right. So the last part of this is just thinking about this problem, the way that you would put it all together in a particular, like a free response question. You might be asked this type of question like we went through before, and you would have to identify and say, when we check the conditions, that yes, we'd have to check the condition here that it's random, which would tell us that the mean is on target. We have the 10% condition, which then says, hey, it's reasonable to assume that this is the standard deviation. And then we'd need to know also that it's a large enough sample. And again, we would assume here that probably stores are going to not be normally distributed when it comes to price. We're going to have a few stores that are really expensive, and we're going to see that because of the central limit theorem, since n is greater than 30, we're going to see that the shape of this is approximately normal. So that put together, we can use precisely what the mean and the standard deviation are of the samples, and then you would normally have to state this in a sentence, right? The sampling distribution of the grocery store bundle means, is approximately normal with a mean of 194 and a standard deviation of $4.67. So when we describe a sampling distribution, typically we're going to give a sentence with that. And then the second part of this question might be, what we did before, where it's calculate, that it's 201 or higher. And if we do that, there's again a 6% chance of getting a random sample of 31. So again, notice that if we had a different sample size, it would be a different sampling distribution. It would be, maybe less variable or more variable depending on the sample size. So we're going to do a little bit more of this probably spend an extra day on it, but at least you'll have a chance to perhaps look at some of the homework in 7.3. So have a great day.